Kappa model with stochastic price. So, obviously prices are stochastic, means they are non-deterministic, and the time factor also comes. So, there is a subtle difference between what is a probabilistic and what is stochastic one. In probabilistic is basically simply that it is non-deterministic, but the values which are there in front of us, like when you roll the die, the values can come out to be 1, 2, 3, 4, 5, 6. But in the stochastic sense, the time factor would also come into the picture. In that sense, the time would also play a major role in trying to find out what is the outcome, depending on what type of decisions which you have, whether they are stochastic or probabilistic. So, Kappa model with stochastic price would mean, if you look at this again, is exactly the same thing. Here you had basically the expected value of the price at time t is equal to 2, which is some time down the future, and then the next term which you have in the numerator is basically the price as of today. So, what you are trying to find out is basically you are trying to find out in some way the R. If you remember, Ri was basically equal to I1 minus I0 by I0. So, exactly the same thing which is being drawn here. And on the right hand side, again you have risk free interest rate. So, this, if risk free interest rate was brought here, it will be the excess return of that particular portfolio over the risk free interest rate. So, just to avoid confusion, the values, whether I use the symbol small r or capital R, they are interchangeable. So, in this case, if I am trying to find out Ri, small ri, obviously this should also be small ri. If I am using the concept of capital Ri, then obviously this should also be capital Rf. And on the right hand side, again you see the same thing, beta is there, which is basically a proxy of the risk, and again in the numerator and denominator the same values are there. This is the excess return of a particular market over and above the risk free interest rate. So, you are trying to basically draw a simile between that, considering the stochastic price and trying to basically analyze the price change with the market with respect to the portfolio of the particular index. The factor given below, which you have here, is basically the risk adjusted interest rate. So, because that would basically be adjusted in such a way that any increase and decrease on the prices would be mimicked by utilizing this concept. So, when we have investment in the concept of investment on the portfolio, if you have linearity to the pricing, it means there is no arbitrage. What is arbitrage? How you make profit in arbitrage? Why arbitrage is used, rather than basically trying to bring a parity in your risk return profile or trying to basically reduce your risk, that would also consider later on. And certainty equivalent form would also be considered, where it will give you a certain value based on which you can find out what is the value of your particular stock. So, if you consider, and you remember the utility concept, what we consider the expected value of the utility given some value. So, what you will do is that replace that probabilistic or the gamble or the lottery with a deterministic case, and the value of the deterministic based on your utility function would basically be considered as a certainty equivalent based on the fact that a lottery which you are trying to formulate for the certainty equivalent has a probability of 1. In the Kappa model, we have considered the returns are normally distributed, which means the utilities based on which you are trying to find out the returns are quadratic in nature. In case they are log normally distributed, then the modified Kappa model is given. So, till now what we have considered for the Kappa model, if you remember the sin index model, we mentioned time and again the distributions of Ri's, Rm's or Y's or X, whatever it is you are trying to denote as the set of random variables which are dependent or independent, whichever it is, they had normal distribution. And also, if you can recollect, I did mention normal distribution has some properties such that convex combination or normal distribution would always result in a normal distribution. But in case if they are log normally distributed, then you have the Kappa model as given. So, again it has the same replication, but in this case you can find out that is basically the excess return being given such that you have to find out the excess return with respect to its own particular return, which is ERI and ERM, and where beta, where you find out initially, is basically given by this formula considering the log normal case. We would not be doing any problems exactly with the beta what you have found out, but we will consider later on how our betas can be found out for the simple normal distribution cases. Now, we will consider other portfolio selection models. So, generally investors have the following characteristics. Whenever you are investing, till now we have considered concept of non-cessation That means more I give you, more you want, and you are risk averse. So now we will consider the expected utility maximization is true, that means you will prefer more to less, which is also equal to the concept of non-satiation, but now we are considering the concept of utility functions. Utility functions would be considered and you will find out the expected value accordingly. And it also consider the concept of only risk aversion. Later on we will combine both expected value along with risk aversion, expected value along with standard deviation, expected value along with beta, whichever it is, depending on how the risk return profile need to be looked at and what is the actual the concept of risk based on which the particular person is trying to analyze his or her portfolio. Even if you have other forms of utility function, yet quadratic approximation gives us better practical results than in the case of when non-quadratic utility functions are used. But the point of better results has to be taken with a pinch of salt, in the sense that when you are trying to analyze the Newton's laws of motion, we always consider them to be true in the sense that no friction is considered, but still we get very good results. It is exactly the same thing. We will consider normality to be true when, even though it is not true, we will see that the results which we obtain considering normality to be true for the returns, that is considering the utility function to be quadratic, still we will get very good results in order to basically be able to understand the practical situation what is happening in the market. Later on we will try to, at the fag end of the course, we will consider the concept of extreme value distribution. We will try to analyze that actually the portfolios, actually the indices, actually the options, futures, forward, whatever are there, when combined together, when you try to find out the returns, they are skewed either to the left or to the right, depending on what you are trying to analyze, whether it is a positive return or a loss, such that those expected value distributions and the EVDs or extreme value distributions we try to utilize would be used in such a way that they would give us much better results in the practical sense, without losing the flavor that how normality did give us a good picture about reality, even though that was not true. People have other criteria also, as I mentioned in the last slide. So what are the concepts? People can basically analyze from the geometric mean returns, they can analyze from the safety first criteria, they can analyze the problem from stochastic dominance, they can analyze in terms of characteristics of the return distributions also. So rather than, for the last point, rather than only considering the expected value and the variance, you can also consider the expected value and the, say for example, the third moment, or the second moment and third moment, or the third moment and the fourth moment, where the third moment and the fourth moment are basically the skewness and kurtosis corresponding to a particular distribution. For the geometric mean returns, for the selection process we consider the maximum GM, that means geometric mean. So the highest probability of reaching or exceeding any given wealth level in the shortest possible time, that will be considered, and the highest probability of exceeding any given wealth level over any given period of time. So if these both concepts are true, then we will find out that the geometric mean gives us much better result than the arithmetic mean. Arithmetic mean means the expected value or any other criteria based on which we are trying to analyze a particular portfolio. Now in the geometric mean concept, consider this very simply. You have the returns. So this capital R or small r is immaterial, you can consider the returns as it is. So there are now two suffixes. In the suffix which you have is I and j, which I is the possible return of the jth portfolio. So what you have is basically the portfolios are given as well as the outcomes of the portfolio which you have, which can basically be with respect to time. So rather than I, you can have the tth time frame also, which is basically a counter. So what you do is that you try to find out that how many such times that actual outcome has been true. So if you consider the probabilities are given, that is P1j, P2j, so on and so forth, till P and j, considering the fact that the sum of the probabilities is always 1, then the geometric mean is given, GM is given by this formula, where you basically find out the returns. 1 plus r means basically you had some value of a, and that value as a is increasing by the term a into 1 plus r, in a simple concept, and then they are being raised to the power of the probability they are. So this is exactly the same concept as you use in geometric mean. Minus 1 because you are trying to find out the value of the excess of the portfolio. So Pij is the probability, the ith outcome for the jth portfolio. Then once you find out the values of the GM, you basically choose the maximum geometric mean based on which you take your decision. Consider we have the following combination of assets A, B, C in the following ratios or the weights. So, ratios are basically WIs. The returns are 10, 20, 30, and for A, B and C the first, second, third column gives you the situation. So, if you find out P RP1, that is for the first instant, RP2 for the second instant, which are the rows, and RP3 for the third instance, obviously you will have the returns given as 10, 20, 30, which we are considering as fixed. It can change depending on the situation. So, in the first case it will be to the power of 0.2, B would be 0.2 and C would be 0.6, such that if you see the probability sum up to 1. For the third case the powers are 1/3, 1/3, 1/3, again the sum has to be 1. So, if you find out this geometric mean, then the value comes up to highest for the first case, hence you choose the scenario 1, which will give the highest return, considering geometric mean is your main criteria based on which you will take your decision to invest in that portfolio. Maximizing geometric mean is equivalent to maximizing the expected value of the log utility function. So, now going back, we said utility function being quadratic, you had normal distribution. Now, if you consider that you are trying to basically have the log utility function to be true, then trying to find out the geometric mean and trying to maximize would give you the same answer. So, this is basically in a very simple terms, there is one-to-one correspondence between quadratic utility to normal returns and log utility through the concept of geometric mean to be true, based on which you can find out the excess return. Portfolios that maximize the geometric returns are also the mean variance efficient if returns are log normally distributed. So, if you consider that in one case you are considering the risk return framework and trying to take the maximum return and the minimum risk, and in another case if you have basically a log normally distributed returns and then you find out basically the geometric mean and basically maximize the geometric mean and take that portfolio. So, the answer which you get in the second case where you take the log normal return, and the answer if you get in the case when you consider the utility function to be quadratic, they would be almost a one-to-one similarity between them. So, whichever concept you follow, you will obviously get the same answer in trying to rank the portfolios depending on different criteria. Now, the second one we will consider after geometric mean is the safety first principle. The basis tenet is that the decision maker is unable or unwilling to consider the utility theorem for making his or her preference. That means, the person is not sure about his or her utility functions, or you are not not sure about the utility function of that person, and you will take the concept of safety first principle in order to basically analyze the outcome based on which you are going to take the decision. Under this methodology, people make the decision placing more importance to bad outcome. That means, worse it is, you basically put more weight. It is like this: if I get good results, I am okay, happy, but if I get very bad results, my overall tension level is very high. That means, I would basically lay more stress on negative returns rather than being happy on the positive returns. So, obviously, I will try to analyze the situation, in each case I would definitely not want any negative returns, but if positive returns come, I would be happy, but not that be elated in the sense as I am very sad, as in the case when the negative returns are possible. So, the safety first principle consists 3 different criteria, sub criteria. One is basically you minimize the probability of the portfolio returns being less than equal to some stipulated returns, which is RL, first case. Another case is basically you maximize the level of criteria based on which you are trying to invest, which is RL. And the third case is basically where you maximize the RP, so the return of the portfolio. So, you should remember something that the value of RL and the value of RP which you are trying to analyze are not the same. So, RP may be the actual value of the portfolio which you have, but RL may be the value of the portfolio which you want that portfolio to reach. So, say for example, you want your overall portfolio for the number of stocks which you are trying to analyze to be, say for example, 20%, but your portfolio value can be 15%. So, in whatever case you are trying to analyze, it may be either you want to basically increase the return of the portfolio or increase the overall threshold value RL over which you would like the portfolio value to be. So, these are 2 different situations where you are trying to analyze the same situation in 2 different cases or trying to look at it at 2 different angles. So, if returns are normally distributed, then the optimum portfolio would be the one where RL was the maximum number of standard deviations away from the mean. So, let us consider an example of the first case which you are trying to minimize RP less than equal to RL. Remember, we consider the returns are normally distributed with the suffix p denoting the portfolio, while RL means the fixed value of the return. So, what you are trying to do is like this, you have a return which are normally distributed, remember it is normal, and you have the average value of the portfolio. So, this average value of the portfolio is given by R p bar, again small r, capital R does not matter here. So, what you have done is that you have fixed some value of RL, this is the RL which you have done, and this random variable RP is such that you are trying to basically find out how far it is from the RL value in terms of standard deviation. So, if you expand this formula using random variable to be normal, what you are doing is this, probability of RP minus RP bar by standard deviation is less than equal to Rn minus RP bar by standard deviation of P, which means you are trying to convert those values into a standard deviate or a standard normal deviate case, where this is the random variable z and this is the realized value of z depending on what is your level of significance or the number of standard deviations far away it is from the actual case. So, consider this RP is 10, 14 and 7 and standard deviations of the portfolio are given at 5, 4 and 8, then the difference with from 5% are given by one standard deviation 2.25, 1 1.5, which means that how far the dispersion is. If the overall dispersion is 2, so that means you are going plus and minus 1 to the right and the left of the mean value. If it is basically 4, you are going plus and minus 2 value onto the right or the left of average value RP. Similarly, if you have plus minus 6, you will basically have plus 3 and minus 3 depending on which side you are going. Now, the level of the difference which is 2 sigma, 4 sigma or 6 sigma would basically give us that concept such that you can find out what is the overall dispersion. So, if it is 2 sigma, overall dispersion is average, I am giving you very average values is 67%. If it is basically 4 sigma, it is about 97%, and if it is 6 sigma, it is about 99%. So, it means that if you have this graph and consider the RL value is given. So, and your actual distribution is given by this or by this, whichever it is, I will consider one at a time. So, in the first case you have with the bold normal distribution returns are there, which is the bell shaped curve. So, this is basically removed from RL, this average value, by this distance. But what you are trying to do is that you are trying to basically minimize or maximize the differences depending on which side of the graph it is. So, if you go more on to the right, then the corresponding probability of the differences obviously will increase, which you want. If it is on to the left, you will try to basically bring it RP value as close as possible to RL such that it is minimized. So, in this case, depending on the standard deviation and the expected value, standard deviation would be basically given by the dispersion on the left and the right hand side. So, what you are trying to do is that you are trying to basically either find out the ratios in such a way that the value of RP with respect to RL is either maximized or minimized depending on which side of the curve it is, such that you will try to basically gain the maximum amount of probability such that the returns are increased to the maximum possible extent, such that you are more concerned about negative returns and less concerned or less happy about basically positive returns. In order to determine how many standard deviations RL lies below the mean, we calculate RL minus the mean, and then once you find out, you basically find out what is the ratio. So, if you consider this value, this RL minus RP divided by standard deviation, or if you change the sign, it becomes RP minus RL divided by standard deviation, and this is equivalent to exactly this. So, what you are trying to do, you fix up some RL value. So, now you will ask what is the RL value. Let us consider it is the risk free interest rate. It can be risk free interest rate from delta value also, that does not matter. So, what you are trying to do, you are trying to basically analyze the portfolio, rank them according to the principle of excess of that particular portfolio with respect to the risk free interest rate divided by the standard deviation of the risk, and rank them from the positive to the lowest, to the highest to the lowest. So, if you go back to the principle which you have already done, it was either Ri minus Rf by standard deviation or standard deviation being replaced by beta. So, whichever you look, now this different perspective of this ranking of extra return to risk free interest rate divided by beta or by sigma is basically a concept of safety first principle, where you will consider that if it is normal distribution, it is easier for you to analyze the problem in a simple sense, where you use the standard normal deviate and the tables and the charts to find out these values. Even though for our example we have simplified our assumption by considering only normal distribution, but this would hold true for any distributions depending on that they have the first and the second moment, because the first moment is the expected value, second moment is the variances. For what we are trying to do is find out the expected value minus some RL divided by the variance of RP, which is the second moment, and rank them accordingly. So if you have, rather than normal distribution, if you had a graph of this, so this is the mean value and this was the standard deviation and the variance, you will basically find out the ranking based on the same fact that what is the excess return divided by the risk and rank them from the highest to the lowest. Another thing can be that rather than trying to rank them from the highest to the lowest, it can be done the other way around also, but the question is that how would you do that? In that case, rather than take the excess return to the over the risk free interest rate and divide by the value of standard deviation, what we will do is that we will rank the ratio of the variance with the respective value of excess return. So now we are trying to basically put the risk on the numerator and the return on the denominator and rank them from the minimum to the maximum and take the minimum value. So now if you can recollect, in statistics we have the Chebyshev inequality. The Chebyshev inequality basically means that given the two moments, the expected value and the variances, then the difference of the random variable with respect to its expected value divided by the standard deviation, if it is greater than some t value, whatever the t is, then the probability is given by this formula. So if you look at this, it is exactly the same thing. What you are trying to find out is you are trying to find out the excess value of that particular stock random variable with the expected value divided by the standard deviation, and that value is greater than some k value depending on what your safety value is. So if your safety value is very high or very low, then the probabilities have to be adjusted accordingly. So if the probability value is very high, it will give you a picture that whether you are really conservative, and the probability value is very low, obviously it means that you are not that conservative. That means your safety level based on which you will invest would change from person to person depending on his or her utility perceptions or the risk return values. As we are interested in lower limit, hence we simplify it. After simplification, if you see that on the left hand side you have basically the excess value over the return value, average value, and the left hand side you basically have the excess of the risk free interest rate or the RL value over the RP value, and that should basically give us in a way a concept of the variances of these two cases. So if you find out the numerator is the variance of that particular portfolio, and in the denominator is basically the variance or the differences between the deviations or the minus values between the return which you want that particular portfolio minimum to have, which is RL or RF, minus the average value squared. The why you are doing a squared one, because you want to find out the ratios in the variance sense. The right hand side of the inequality is exactly equal to the decision process number 1 under safety first principle. So once you simplify, you get the probability that the RP value is less than RL or greater than RL, depending on whether you are more concerned about risk on the negative side or so called risk on the positive side, which is positive to you. For the second criteria, which we consider maximization of RL, we consider the probability to be such that there would be a constraint which will be given by probability of RP being less than or equal to Rn is alpha. So higher or lower alpha would basically give you the confidence level. Alpha as 0.05 or 0.10 or 0.15, then we basically should have considering normal distribution as this. So what you have is basically this would be the small z value, as I have already discussed. This would be the capital Z value, which is the standard deviate. So if you have the distribution, this is the value of 0 because the expected value of the z value is 1, and what you want to find out is that how the deviation is based on which you will take a decision. So if this is small z, you want the return of that particular portfolio, excess return in the sense RP minus RP bar, not in the excess return of the sense of the RF, but excess return divided by standard deviation. In this case, out of these 100 cases, only 5 number of them should be on the left and the 95 of these cases should be on the right. So, this 5% or 0.0 number which is coming is basically giving you how many number of times it would be on the left. So, if this value is say for example 0.005, it means out of the 1000 such runs which you do or the 1000 such scenarios which you generate in the portfolio, 5 numbers of them would lie on this side and the rest 1000 minus 5 would basically lie on this side, such that you are always happy that out of the 1000 such instances only 5 are not favoring you, the rest are favoring your outcome. So, this is the scenario which you have drawn. Consider is a normal distribution for 0.05 is on the left and any deviation on the left is definitely not wanted, you want to minimize that. Any deviation onto the right, right means this portion is good for you. So, you are trying to minimize the number of chances of occurrences onto the left. Now, this implies that depending on the value of the standard deviation. So, what you want to do is that you want to have RP bar greater than or equal to RL, which is the fixed level which you have put for yourself. It can be again RF, and if this is 1.65 times into the standard deviation, that means you have a value of RL and you want to basically move away from the RL onto the right 1.6 times more than the standard deviation. So, higher values are good for you, lower the values is definitely not good for you. Change the fixed rate of return, that means change RL as RL1, RL2 like as you did RF1, RF2, RF3, RF4, so on and so forth. And once you do that, you basically have different scenarios based on which you can basically rank them. So, what you are doing is this, again the straight line is there and then you keep changing, that means you are doing you keep changing RF1, RF2, RF3. So, all of them are parallel. Why they are parallel? Because none of the values are changing. So, it is basically RL1 plus 1.65 into standard deviation, RL2 plus 1.65 into standard deviation. So, the values of standard deviation and that 1.65 value which you have put depending on level of confidence is same. So, as you keep changing them, they are all on parallel lines, and the point where it touches says the efficient frontier is exactly the value of Q which you have done already or the market value which you have done. So, in a way the concept of safety first principle, the concept we are trying to basically use the Kappa model, the concept we are trying to use the utility function as quadratic, the concept we are trying to increase the return and minimize the risk, all lead to the fact that they give you the same set of results or same type of result based on whichever outlook you are trying to basically find out. Now, the third criteria is basically maximizing RP. So, you basically maximize RP again set to the same conditions where you try to find out the probability of RP is less than or equal to RL some alpha value. So, obviously, alpha value in the long run should be made as small as possible. Here alpha is the predetermined value depending on the investor's own constraints. Thus, with the condition we can easily find out that RP should be greater than or equal to RL plus Z into sigma p. So, this is the value of the Z which you have put for yourself 1.65 or 2.0 whatever it is, depending on that you basically try to find out. So, in the first problem you had basically the safety first you want to minimize, and in the second case you want to basically maximize RL, third case as it is you want to basically maximize RP. But one interesting fact is that both for maximizing RL and maximizing RP you always use the same constraint, which means that you are trying to basically use this equation in such a way that the return of the portfolio RP star is greater than some fixed value RL or RF whatever it is by a certain distance. That distance which is basically K or Z into sigma p would be dictated by two things. One is the standard deviation of the portfolio which you have and the level of confidence which you have or the level of risk perception you have about this problem. So, again in this problem now rather than changing RL you change the value of K or sigma, which is basically so called slope of that line. If you keep changing it starts moving and at some point of time again it basically is tangent. So, again this value is Q. So, the value of Q which you obtained by using this equation either changing this such that they are parallel or changing this such that line moves anti-clockwise gives you the same point of Q such that you can find out the Q in all the cases. So, now there are three forms of efficient market theory. One is the weak form, one is the semi strong form and the strong form. In the weak form, you cannot predict the future stock prices based on the past information. That means stock prices behave very much like the random walks. Semi strong forms, you cannot utilize published information to predict future prices. That is, the basic notion of semi strong form goes against the fundamental analysis, and the strong form means nothing, not even the unpublished or published informations can be utilized to predict the stock market. So, in our case which you are trying to analyze, we will consider the prices to be such that whatever information is there is easily available to all of us, and the market mimics the actual reality to the maximum possible extent.